Hi, everybody, and welcome to assignment 3. And so I have with me today Jianan, who's going to tell us more about himself. Just a brief introduction. We're here for the AI Clinician Champions Program. It's also AI in healthcare and a number of other general AI in healthcare programming that we run. My name is Shingai, and I lead professional development at the Vector Institute. I'm a director there, and I'm also the course director for this program. So together, Jen and I have created this fun case study and tutorial for you. But before we get there, Jenan's going to take us through his code, and he's going to explain what he was thinking and computer vision in general. But before we get to that, Jianan, who are you? Tell us a bit about your background, your research. How did you end up here? And then take us into the code.
Okay, so hi everyone. My name is Jianan Chen. I'm a first-year PhD student at the University of Toronto. And before my PhD, I had a master's degree in artificial intelligence, and then I decided to switch to medical imaging in my PhD because I want to sort of bridge the gap between the theoretical research of AI to the clinical applications. So so in my work, I work closely with clinicians from Michener Institute to stratify cancer patients using liver MRIs. Yes. I look forward to working with you in this course.
Yeah, and we're very lucky to have you because you're the real deal. You are both AI and machine learning, as well as starting to look at specifically clinical applications of this work. All right, so you can put up the model for us, and we can get started learning more about computer vision.
Okay, so can you see my screen?
We can. Do you want to make that just a little bit bigger, the font?
Like this?
Yeah, that's just a bit better. Yeah, cool.
Okay, cool. So in this assignment, we will look into the application of computer vision in medical data. So in this assignment, we focused on melanoma classification. And so basically it means that we we train an AI model that look at images of skin lesions and predict whether the lesion is melanoma or a benign skin change. So so we focus on melanoma here because it's a very it has a lot of cases each year, and it leads to about 7,000 deaths each year in the States alone. And then if we can detect melanoma earlier, we will be able to provide better treatment or save patients' life. So in this case study, we used a dataset from Kaggle, which is a popular website for machine learning challenges and datasets. And here we used a subset of the dataset because the original dataset is very big, and then it will take a few weeks to train a model. So in this case study, to help you see the whole process of training, so we only used a subset of 600 images for training the dataset. So let's get started. So I assume you will be familiar with Google Colab from the first case study. So what is different here is that because we are training a neural network here, we want to enable GPU, which means that we want the Google Colab to train our model using GPU provided by Colab. So to do this, you have to select runtime here, and then change runtime type. And then it might be none for your Colab notebook, but you have to change it to GPU and press save. So in this case, you will train your model much faster because GPUs are, there are some specific designs in GPU that are accelerating the training of neural networks. And yeah, if you press the run cell button here, it will says device available now CUDA. So CUDA means the GPU. So if you see this, you will know that you made the correct setting. And yeah, so for the rest of my notebook, it will have the similar format where you will have the code on the left and the description text on the right. So if you want to hide the code or show the code, you can just press the three dots here and then select hide code or show code, which will yeah, give you some information if you're interested in the code. And after that, we will first import some Python packages for processing images. And in this case, the images we are using here is natural images taken by the cameras. So we use a package called OpenCV for natural images. But I know that in your work, you will probably work with other imaging modalities like MRI, CT, or ultrasound. In that case, you can use other Python packages like SimpleIDK or PyDICOM, and these are designed for the DICOM format of medical images. So I just included the documentation of these packages as a pointer for you. So if you are interested, just click on the link and it will lead you to the website. Yeah, so then we want to download the dataset and save it in Colab so that we can use the data for training our model. What we did here is that we stored the subset of the dataset as a zip file on Google Drive, and once you run the code here, it would automatically download the zip file for you and unzip the data for you. So if you press this, as you can see here, you will be downloading this zip file. And if you want to see the actual images or the spreadsheets, you can press the folder icon on the left, and then you will see the files you downloaded, and you can potentially download one of the images to local to see them. Yeah, and so next we imported some other packages for the training of neural networks, and in this case we used a framework or a package called Pytorch, and this is very popular among researchers. And I personally, this is my favorite package because it's very easy to adapt to my own workflow. And it's very well documented. And again, if you're interested, you just press the link here. Okay, so next we will have a look at the dataset. If you run the cell, you will see that we had 600 images in total. And in this experiment, we used 70% of data for training and the rest 30% for testing. I believe Devin must have told you about the importance of splitting data into training and testing cohorts. And so we have two types of data here. So first, we have a spreadsheet that includes the ID of each image, and then also like the target we want to predict is the lesion benign or malignant. And then the other type of data is, of course, the images. So as you can see here, we have 5 images, and 2 of them are benign and 3 of them are malignant. And then before we start training the neural networks, I had some code for setting the random seed of our code. So what it does here is that it makes sure that every time the random number generator generates the same number, so basically your results are reproducible if you set seeds for your experiments, and this is very important for AI research.
So Jianan, before you carry on, can I maybe just recap what I've heard you say so far? So we're here to run an image classification model, and your data set is photographs. So, potentially taken by a phone, camera, whatever. They're JPEG files, and we've got a bunch of photographs in a file, and these photographs are labeled. So you know which of the photographs have melanoma and which ones don't. So yes, that's the database that you're working with. And you said it's a subset of a bigger database because obviously images take a lot of time and resources to compute. And so of the just above where we are now, you actually have some examples of those images. Okay, yeah, fantastic, right? So that's actually somebody took, a photograph of, a portion of their skin, and we're actually working with real examples here. So you've done the separating of training and testing. Yes, Devin covered that, and it's all throughout this course, there's training and testing discussed. And you said 70-30, that was your split? Yep. Okay, yeah, great. So 70% of your data you're going to use to train our model to recognize melanoma. And then the 30% you're going to test to see how well the result model actually does that. So I'm just looking on the left-hand side on your table of contents there. So the next phase is we're actually into the neural network already. So you haven't, your data cleaning and all of that is kind of done for us because you've got a pretty clean database, and we're already into the neural network part of the assignment.
Yes, I would say those images are in JPEG format, which is very good for our training of network because it only needs very little pre-processing. And actually, for the first section of neural network, we will still need to do some pre-processing on the dataset. But I would say it's much easier compared to like real medical images in DICOM format because those need much more pre-processing before we do the training.
Yeah, so some images might need cropping or changing colors or okay, that's okay, got it. Okay, great. Please continue.
Okay, yeah. So for the model we will be using here, it will be deep neural networks. So yeah, again, I think Devin may have introduced you about this. It's basically just multiple layers of perceptrons that takes the original image as input and just output a target, like whether the image is cancerous or not. And so in this figure here, I have basically a summarization of state-of-the-art neural network models in terms of both the number of parameters of those models and also the accuracy of these models on a specific data set. So, so the reason we not only care about the accuracy of the model, but also care about the number of parameters here is because that if the model has more parameters, it means that it requires more computing resource and more time to train. So in the deployment of deep learning models, we not only need to care about the accuracy, but also need to care about like how fast can you train your model and how long is the development process, including like training your model and then getting some results and then see how you can improve the model or correct some errors and run everything again. So you can't like say like I want the best model regardless of the parameters because that may take years to train. So yeah, it's very important to make the trade-off between efficiency and performance here. And in this assignment, we will see the performance of two specific neural networks here, and one of them is ResNet, as you can I assume you can see my mouse. It's ResNet, and the second one is EfficientNet B2. So ResNet is a very popular network structure. It's it's developed a few years ago, but it's still the most popular network architecture for most of medical imaging applications. And for EfficientNet, we use the B2 version, which is with low number of parameters, but relatively high accuracy. So we will compare the efficiency and performance of these two models here. And so let's get started. So we have already downloaded the melanoma dataset, and then the first thing we do is that we need to create a dataset object. So basically, those deep learning framework like Pytorch or Keras, they requires you to change the format of your dataset to a specific format that can be taken by the framework. So so here we use the Pytorch package to turn the JPEG images we had into a format that is acceptable by the network. So as you can see here, we did a lot of pre-processing on the dataset to make them ready. So we have normalized, which means that we make sure the style of the images look similar, because if you go back to the imaging examples, you will see like some of the images have a lighter background and some have a darker background. So with normalization, we make them look at least have similar intensity. And then we have other transformations like resize, because the neural network can only deal with images of fixed size. So those images taken by cameras may have different size, so we need to resize. And we have the other set of transformations here, and these are called augmentations. So the reason why we need augmentation here is because the performance of a deep learning model or a neural network model scales up with the number of training samples we have. So the more data we have, the better the the better the performance will be. So in this case, we did several types of augmentations, including affine transformation, which just zoom in, zoom out, or rotate the image to a specific degree. And then we also have horizontal and vertical flipping. And then we also alter the color of the images a little bit. You will see some examples in the slides, which we will cover later. Yeah, so the reason behind that is that sorry, we go back to the images here. We have skin decision here. And if we flip the image or rotate the image, they will look different, but they will still be the same vision. And it will basically provide more samples for the network to learn. While like in the case that we cannot find more images to train, we can use this kind of techniques to augment the data set we have and achieve better results. And in the following experiments, you will have a chance to tune the augmentation parameters yourself and potentially see the difference caused by the augmentation parameters. Okay, and another thing to note here is that we only do the transformation for training and testing, and we don't do it for validation, because we are only augmenting the dataset for the purpose of training here, and for validation, we just want to see the performance of the model on the real data without augmentations. Yeah, so that's it for the data pre-processing. And then we will define the structures of the network. As previously mentioned, we have efficient net and resident 50. And because these networks are very popular, you can actually find predefined implementations online. So I think it's very convenient if you are interested in some types of techniques or some types of networks, you can just go to GitHub. So it's github.com, and then you just search the network you are interested. Because so, for example, if you want to see other people's implementation of ResNet, you just type ResNet, and there will be lots of implementations of the network, and you can pick one that suits your need. So yeah, so this is basically an implementation from GitHub, and then we use the B2 setting for efficient net here, and we use ResNet 50, which means there are 50 layers of the ResNet. Okay, and then we need to define a function for training the network. So basically, it's just feeding the data set to the model, and then use a loss function and an optimizer to teach the network about our task using loss function and gradient descent. And I don't think you need to know the specific details of these procedures, but if you are curious about any part of the assignment, feel free to come to my office hour or email me.
Just one quick question would be,
yeah.
Can you just give us like in plain language when we talk about the loss function and gradient descent, like what do those two themes mean in the context of a neural net? Just in conversational language, you don't have to get into the technical details.
Right, okay. So a loss function is basically a metrics we want to optimize. For example, in predictions, we in this prediction task, the loss function will be the percentage of correctly predicted samples. So it's just so our when our model is fed sample, it will output whether the model thinks the sample is benign or malignant, and then we compare it with the ground truth, and then we get a percentage of the for how much for how many samples our models achieved a correct prediction. So basically, that's a loss function. We use this to tell our model if it's getting colder or like hotter to the correct model. And then for gradient descent, it's just algorithm for passing the passing the loss function to the network parameters. So what we're doing here is that once we know the network made some wrong predictions on some samples, we need to tell the model how to improve from its lessons. So that's where gradient descent plays role. So it's just a way to change the parameters of the network. Cool. And yeah, so next we will talk about the hyperparameters of the network. So this includes a lot of parameters, including, as we have mentioned, including the augmentation parameters. For example, the probability of doing horizontal and vertical flip, and also like how aggressive when we alter the color of the images. And So apart from this augmentation related hyperparameters, we have others like training related, like number of iterations or epochs we train the model, and also like learning rate of the model, which means how basically how aggressive we update the network parameters when we train the model in each iteration.
So,
and
good question. So how do you know how many epochs?
Yeah, so that's a good question. So for epochs, like in general, we will need a large number of epochs. So basically what we do is that we just set a large number of epochs beforehand, like for example, 100, and then we like once we run those 100 epochs of experiments, we can plot the change of loss and see like how far does it go, like at how many epochs does the model stop learning and is getting stable performance, and then we just basically you just have to do a lot of experiments and pick the most suitable epochs for your model.
But with a vision model, though, that has resource implications. So
yes, and so another thing you can do, and this is also what we did here, is that we can use a scheduler. So basically, a scheduler is that is a tool that automatically monitors the training process of your model, and you set a patience of patience also has a hyperparameter. For example, here we have patience equals 3, so which means that if we haven't seen improvement in performance after 3 epochs, we stop training. So even if we set the epochs as like 1,000, and if the model stops seeing improvement after 5 epochs, it will stop. So that's another way to regulate the training of your network.
got it. Thanks.
Cool. So yeah, so everything is ready, and then we can just train our networks. So we have first we have efficient net B2 here. This is one of the best model in the market, and you can just go to this model first in your own projects if you have, and yeah, there's as promised that there's a way for you to interact with the model by tuning the parameter here. So you can by dragging the point on the bar, you can just set different values for the augmentation parameters, and then you can run this experiment. And so once you are set with those 2 parameters, you can press a button and run your experiments. And so we have a small data set here. So each epoch will only take about 2 minutes. So we have 10 epochs, which will take 20 minutes in total. But depending on the GPU you're getting with Colab, it may take up to 50 minutes. But what you can do here is that you can monitor the bar at the bottom. It will tell you like the model is working on something, and after about 1 or 2 minutes, the results will be printed here, and you can have a look at the results.
So Jianan, when I was running your model, at some point I got stuck and I was doing other work on a different screen, and I saw nothing's moving. And then I checked, why is it taking so long? And then I realized I hadn't used the GPU. So that was immediately an issue. So then I did that. And then I started running it again. And then I got an error message that said, too many sessions open. And that's because I was looking at multiple Colab files. So I thought, oh, okay, I have to close some and then rerun it again. So that's just a warning to anyone who wants to try the code, that just keep an eye on it, right? Because it should run. And if for whatever reason it gets stuck, sometimes you just have to restart it and go again.
Yeah, exactly. Okay, so this may take 20 to 15 minutes, so you can leave it alone and do other stuff. But remember to come back after the expected time, because if you're inactive on this page for too long, it will like die and you have to restart everything. So, and we are currently running our model for about 2 minutes, and you will see, yes, you will see the results printed here. And so for each epoch, we print the current loss and the training accuracy and the accuracy on the validation cohort, and more importantly, the ROC, which basically is the AUROC, which is area under receptive operation curve. So this is what we mostly use for classification tasks, because you might ask, why don't we use accuracy? But in real world tasks, we most of the case we have imbalanced data set. So having a high accuracy doesn't mean your model performs very well on like in terms of specific classes. Sorry. So, but ROC here is a combination of sensitivity and specificity here, which are more clinical relevant in your task. So we would almost always prefer AUC as a matrix for evaluating your model.
Another question is, I didn't see you specifically separate any validation data. So you said 70-30 training testing. So how is the validation split happening?
Right. That's a good catch. So I think I have.
So if you remember, those of you who are, okay, great. If those of you who remember, with training and testing, you have to separate out a batch of the data for the training. And Jianan said we're using 70% of the data for that. And then he said the balance of the data set is 30%, and we're going to use that to test to see whether that 70% training part worked well. But then now he's talking about there's a validation component. So he's going to explain to us what that is and where that is established.
Yeah, so here we have three parts of our data set. We have train, validation, test. In the machine learning community, we almost never touch the test set. We don't do anything to it. So we don't want our model to see the test set at all. So when we train our model, we don't test the performance of our model on the test set. Instead, we use a proportion of our training set. We just separate them as the validation set, and then we only test the training set. We only test the performance of our model on the validation set to like mimic the test set, but we never see the performance of the test. So it's expected that if your model is doing well in the validation data, it in general will have better generability, and it will also work well for the test set. That's the idea.
Fantastic. Okay, got it. All right, okay, so we're still going. We should have at least more than one. There we go.
Yeah. So as you can see, in the second epoch, the loss function is the loss value is reduced, and the accuracy is improved in both training and validation. And the AUC, it really should be AUC here. The AUC improved a lot. But since the training is done on the training set, and we use different kind of augmentations, and we sample different. We shuffle the order of the training samples, so it's possible that the model has increased the loss of the increased the loss and reduced the accuracy in the following epochs. It's completely normal. Just wait for the model to finish training, and you will probably see the best results at the end of the training. So we will leave it running here, and when we go back, we will probably see the scheduler changing the learning rate and maybe early stopping the model. This may take 20 minutes, but if you are interested in this, you can set different hyperparameters and compare the results. In general, what I'm seeing from the training of the dataset is that we will get about 0.85 AUC, which is, I think is not bad in this kind of task. Because if a non-expert does this kind of task, like a human will also achieve a similar performance. And this part is optional, but you're welcome to run this comparison of ResNet and see the how compare the ResNet model with the efficient net model to compare the both the efficiency and the performance of the two models. And as we have seen from the figure, the ResNet model will probably take longer to train, but have slightly worse performance.
Okay.
Oh, we have the rest here. So AUC is around 0.81, and then in this case, it's taking the same time, but it may take longer in different experiments. Yeah, so that's it for training the network. And an important factor in computer vision tasks and also in AI tasks is the integration of the neural networks. Because people always say that the neural network is like a black box. You feed something and it outputs something. You don't know anything that is happening in the middle. But actually, it's a very active area of research for AI researchers. And then they have developed various types of algorithms that can help us understand what's going on in the middle. So here we have, we use GradCam as an example here. And similarly, so you can search in GitHub and you will see those implementations of these techniques, and just you can use those code directly, or maybe change it a little bit according to what kind of model, what kind of neural network structure you're using. So yeah, so in this block, it's very long, but we are just defining this algorithm and prepare it for our model. And once we have defined the GradCam technique, we can use this to visualize the activations of the networks. In other words, we will use this to show which part of the image is the network looking at when it makes the prediction. So we basically defined another data loader, if you recall, when we do the training of the network. We just defined a data loader to load some example images for us to visualize. And as you can see from the results here, so each image on the left is skin lesion image sampled from the data set. And in the second image here, we have the activation of the network, or the region of interest of the network. And in the third image, we have the activations overlay on the original image. And you can see that for this image, the network looks at this part and makes a prediction that about whether it's benign or malignant. And similarly for this one, the network is focused on the middle of the skin lesion. And but for this one, you may see that instead of focusing on the lesions, it actually has high activation along this line. And this is obviously an artifact of the image, probably the measure of the camera, but it's definitely what we want the model to look at when it makes the predictions. So by using this kind of techniques, it helps us understand what the network is doing, and then once we know that it's looking at these artifacts, we may have solutions to make the network on the right track. So like basically just once we identify the problems, we can solve them. For example, in this case, we can simply exclude this image, or like we can remove this thing from the image. And this is I personally really like this type of techniques, because in some cases the visualization technique not only help us identify the problem of the model, but also can sometimes lead to scientific findings, because like when we for example, when we use a model to predict the survival outcome of patients, this kind of technique will potentially help us identify the part of the, let's say, the tumor that leads to the worst prognosis of patients, which has a lot of clinical significance. That's it for the interpretation of networks. And at last, I want to discuss the performance of the model. So as we have mentioned, our model trained on the small subset of the dataset achieved 0.85 AUC. And I would say it's not too bad because it's similar to human level performance, like non-experts. But we can see from the leaderboard of the challenge that the winning team actually got 0.95 AUC using similar techniques, but trained on the whole dataset, which consists of 60,000 images. That's a lot. That's like 100 times more data. And if you recall, our model takes about 20 minutes to train, and if your time is with 100, it may take a week or two. So yeah, it's at the end of the day, it's a trade-off between efficiency and performance. And we, like in this case, we also have the whole dataset, tens of thousands of dataset available. But if you want to train on more data, you actually have to go collect those data, which is very difficult because of like various problems, like variabilities in imaging protocols, and also ethics and so on. So yeah, so it's a difficult problem. And from my understanding, I think the model is not ready to be applied in clinical yet. One reason is that, as we can see, it's sometimes looking at different, the wrong parts of the image. And also, in this case, if you have a look at the images, you will find that most of the skin lesion images are from Caucasian patients. I mean, it's the disease is most popular in Caucasian patients, but other skin of color people will also have this kind of disease. And if you, I have included a reference of a paper here. So if you, I suggest you read it. So if you read it, you will find that for people of color, their skin lesions actually have different clinical presentations. They may look completely different, and they may occur in different sites, and they may also have different prognosis. So if you imagine we applying this model in clinic, it may not work very well for those patients from other races, because it has never seen the data. So it's expected that it doesn't work very well for unseen types of data. So yeah, easy fix for this is that we can add skin cancer images from people of color to our training set, and the model will figure out a solution to predict the malignancy of any types of data. But I tried very hard to find those kind of data sets, but actually I couldn't find any on the web. So yeah, it's a different problem, and I'm not a clinician here. I don't know very much about the disease, so it's very important that you clinicians design your own problem and find the potential biases in the data set and collect the right data for training the right model. And yeah, it's impossible to train a good AI model for clinical purpose without the knowledge of clinicians. So yeah, I hope you run through the notebook, and I hope you can learn something from this week's case study.
Fantastic. Thank you so much, Jianan. That's really, really helpful. You really outlined the entire computer vision model. And we're starting to build an understanding of regression, computer vision, and then ultimately we'll look at the natural language processing model. So we really see hands-on how these models work. Okay, I also like the point that you ended on, which is that we need clinicians who can help us with these models, because somebody who's running a model from a more computer science background without that clinician context may not know some of the nuances that go into diagnosing this type of disease. And then, of course, the issue of bias, where data sets that you could find were typically of light-skinned people. So when we're now trying to apply the same model to dark-skinned people, it may not work as well. So really important point to end this on. So that brings us to the end of the coding section of this assignment. We're going to pause here. So next steps for you are to watch the video on the PowerPoint, and then you can actually get started on your assignment. And, we will read whatever you submit. And we really want you to take a moment to be thoughtful about what a model like this can mean if it's deployed in a clinical setting. All right. Thanks, Jenna.